It's raining out there. It's actually. That's one thing I learned. Nobody do. It's really weird, right? Before we got there, you should actually civilization. Contemporary fields. They would only.
Does that stay on YouTube?
Yeah.
It says so. It's based under our account.
Yeah.
Okay, it's good. Yes, it does.
I'll be right back. What time is it?
Other potential employers could look at it and say,
I don't think so.
Oh, there it is.
Which rabbit holes are going
you made an announcement.
I thought that was the one that
live nearby? Where you used to? Okay. You heard about this?
A friend of ours sent us an invitation.
Good. Well, you're in for a real treat. This is really one of a kind thing. This is something really new we're doing here at NASA. Search for life in the world. So for the first time, figured out how to build a telescope to look for Earth twins, signs of life. So we figured out this is our first time. They're all wrapped together into a story. We just had a team meeting here today talking about how to design the mission. A lot of it's online already, and I think Q&A, I think the link or something like that. Space mission. There's just a space. Prettiest spacecraft. Show you how they build that position between you and the star, blocking the light from the star, expose the Earth's further than the other stars. So they figured out how to do that. That's the Starshade. This is way better than the cosmos. It's really happening. What a privilege to be here. Well, but he has a big star. He has a big star, but you know, you can go.
I've taken some of his courses, on this
Right there. This is a lot of emails. Right. That's fine. That's the reason why. This gives us some hope.
What's happening here is
Yeah, the batteries.
See, is this, can you hear me fine? Good. Thank you for coming tonight. Welcome to the Adler Planetarium. For the past couple days, we have been privileged here at the Adler to host a meeting of the science definition team for NASA's XOS, or Starshade mission. And they have graciously offered to share their knowledge and enthusiasm with us in one of our ongoing astronomy lecture series. Look for our next lecture this fall, by the way. As we'll hear tonight, Starshade is an exciting and crazily ambitious plan to directly image planets around other stars using two spacecraft operating in tandem. We'll hear more about this very soon. So both these spacecraft, the Space Telescope and an external occulter, literally a starshade. It blocks the extreme glare from a star so that its planets may be seen. Following presentations from three of the mission scientists, we'll open up to a panel discussion and take questions from the audience. After the panel discussion, we'll invite you to continue the conversation upstairs in the Granger Theater Welcome Gallery. My name is Mark Hammergren. I'm an astronomer here at the Adler Planetarium, and and I'll be your moderator for tonight's event. Now, I'd like to introduce our speakers. Dr. Maggie Turnbull. Dr. Turnbull is an astrobiologist whose expertise is in identifying star and planetary systems that are capable of supporting life as we know it. Until 2012, she led the science team for the New Worlds Observer, a flagship class concept for a space telescope plus Starshade observatory to find and characterize Earth-like exoplanets. In 2008, she started her own non-profit organization to promote space and Earth science in northern Wisconsin and carry out local projects for economic and environmental sustainability. When not thinking about starshades and life on other worlds, she can be found cross-country skiing, keeping honeybees, and tapping sugar maples in the North Woods. Dr. Aki Roberge. Dr. Roberge wears two hats as a research astrophysicist at NASA's Goddard Space Flight Center. With one hat on, she uses telescopes like NASA's Hubble Space Telescope to understand the birth of planets, observing the gas and dust in disks around nearby young stars. While wearing the other hat, she works on the early stages of mission conception, focusing on new questions about exoplanets and planet formation. Recently, she led the exoplanets chapter of NASA's 2013 Astrophysics Roadmap, an ambitious science-driven 30-year vision for the future of NASA astrophysics. Her primary role in the Starshade study is to help plan the observing strategy, estimate the science return from different versions of the mission design, and to keep people from getting too optimistic. Dr. Jeremy Kasdan is a professor at Princeton University in mechanical and aerospace engineering and vice dean of engineering. Until 1998, Professor Kasdan was the chief systems engineer for NASA's Gravity Probe B spacecraft, a satellite test of Einstein's general theory of relativity. His primary research area is in exoplanet imaging from space. Professor Kasdan has led several technology studies for NASA, analyzing both coronagraphs and external occultors. In addition to the Starshade team, he also sits on the science definition team for the First mission, and is principal investigator for the CHERIS instrument, a high-contrast exoplanet spectrograph to be installed on the Subaru telescope at Mauna Kea. Well, I'd like to invite Dr. Turnbull up to begin the first part of tonight's presentation. Thank you.
Thank you.
Welcome.
So much. Okay, so I think all I have to do is press play and we're good, and I'm ready. All right, well, thanks so much for coming tonight through the rain and traffic and whatnot. It's really good to have you guys here and listen to what we have to say. We're going to do a little bit of good cop, bad cop routine. followed by Save the Day. I'm going to talk about how fabulous it would be to be able to directly see Earth-like planets around nearby stars and the things that we can learn. And then my good friend and colleague is going to get up here and try to destroy all my dreams with the reality of why this is so challenging, and it is, and that's why we haven't done it yet. But we can, and Luke Skywalker, Jeremy Kasdan is going to come up and save the day with a brilliant concept for getting it done, or at least opening the door to really a new era in understanding exoplanets and our place in the universe. So I think that, let's see if I figure out how this goes. Oh, okay, I just tap on it. Cool. I'd like to start with this image here. This is the famous blue marble image. To the Apollo astronauts, the Earth in the sky looked like a glass marble, a shiny glass marble hanging in the blackness of space. And this planet, this is the most widely reprinted and redistributed image in history. It was the only one of its kind for a long time. It was the Apollo 17 mission. On the way back home, the spacecraft was aligned with in between the Earth and the Sun in such a way that they could actually capture an image of the fully illuminated Earth. So these cloud formations that you see, this the African landmass, the ocean, this is the same. Every time you see this image, that is the same. You can recognize that. Now we have other images available from high-flying satellites, but for a long time this was it, and this really marked for a lot of people, this really iconifies and marks the beginning of the environmental movement on Earth and the concerted efforts to preserve clean water, clean air, and actually, protect the vast diversity of species of life that are living on this planet. And this planet, in stark contrast to all of the other planets in our solar system, has been broadcasting the presence of life out into the universe. And I don't just mean radio signals, I mean reflected starlight, which has been imprinted with signs of other kinds of life, photosynthetic life, signs of habitability, water, weather systems, clouds, oceans, continents. That light that is traveling out into the universe, if other astronomers could pick it up, they would be able to know quite a bit about our planet and deduce that this planet is habitable and potentially even figure out that there are photosynthetic life forms and other kinds of life forms on this planet. So the fundamental question here really is, that's motivating all of this kind of work, really is, are we really alone in the universe? We know that none of the other planets in our solar system are, at least on the surface, covered with the kind of life that our planet is covered with. But there's other stars out there. And when I was in college, when I started college, we didn't know about planets around other stars like the Sun. The first one was in 1995. That was when we first, had a confirmed discovery of a planet orbiting another star, and it was nothing like ours. But since then, we've racked up quite a few discoveries, which I'll describe in a minute, and started to gradually appreciate that planetary systems are not rare around stars, and perhaps almost all of stars do have planets of some sort. In our own galaxy, so this is actually the Andromeda galaxy here, and it's our sister galaxy, very much like the Milky Way. And what we're looking at right now is a few 100 billion stars in one galaxy, and each one of those stars is a potential site for habitable planets and life. If we zoom out a little bit and look at the Andromeda galaxy, so this is this is a composite image, but it is to scale. So there's the moon, the crescent moon, and you can actually see the night side of the moon too right now. I don't know if anybody knows why, but the reason is because the Earth is so bright and shining on that dark side of the moon. So that's why you can see that when you see a little thin crescent moon every month. And that's the size of the Andromeda Galaxy then to scale. So that right there, that little island of stars, is 400 billion stars. And what just appeared right there, right next to the moon, is a tiny little square about the size of a lunar Maria. And if we zoom in on that, that's the Hubble Deep Field right there. That's a long exposure with the Hubble telescope. And what you're looking at is every single speck of light in there is actually a galaxy. Those are not stars, those are entire galaxies. So that tiny little patch of sky contains, how many thousands of galaxies, each one of which contains hundreds of billions of stars. And it's like that in every direction on the sky. So the universe is filled with so many opportunities for planets and life to get going on those planets that it's hard to imagine that there wouldn't be something out there. So it behooves us to look. Let's talk about hab zones for a second. As you know, the Earth has water on it, and every life form that we know of relies on the presence of liquid water and aqueous chemistry in order for metabolism to occur. And this middle star right here, this is a depiction of different kinds of stars and their habitable zones. The sun, the sun's habitable zone extends from just interior to the Earth's orbit, where much further in, and it's just too hot for oceans to be on this planet. That's why Venus is so dry, even though it's very similar to Earth in other ways. The oceans evaporated long ago. It's just too hot. Moving further out, Mars might actually be in the habitable zone. In fact, we know that there was water flowing across the surface of Mars in the past. If that planet were a little bigger, we could have had 2 habitable planets in our solar system. If we look at brighter stars, so that A star up on the top, that's a brighter star, more luminous. A stars are interesting. They're more luminous, so their habitable zones are further out and wider, physically wider, so maybe you could fit even more planets, habitable planets in that habitable zone. But A stars don't live very long. It turns out that when you're a very bright, massive star, you burn through all that fuel so fast that you have a lot less time for life, for example, to get going, even if a planet is in the hab zone, before that star swells up and becomes a red giant and wreaks havoc on the system. So maybe not the best targets, but kind of interesting. Then if you get too massive, then planets can't even finish forming before the star runs out of hydrogen fuel to burn. On the other end, we have what we call M stars, or red dwarfs. These are faint little red stars that are very numerous in the galaxy, and many of my colleagues are currently having a love affair with M stars because they are so common. There's just so many of them. And we're finding lots of planets around M stars, little planets the size of the Earth, or even smaller. So, but the hab zone around an M star is very, very close to the star. I mean, we're talking like days to weeks for a planet to go all the way around the star that's in the M star hab zone. Interesting, but potentially problematic for other reasons, like probably the same side of the planet would always be facing the star. That might be a problem if you evaporate the oceans off of the hot side and they all freeze out on the cold side and you make a little snow cone planet. But maybe that won't happen, if you have a big enough planet with a thick enough atmosphere. Now the Kepler mission, there have been a few extremely successful techniques for detecting planets. What I'm going to dive into real quick is the Kepler mission. How many people have heard of Kepler? How many people have not heard of Kepler? Okay, so a handful. That means I have to talk about it. So the Kepler mission detects planets by staring at a patch of sky for a long time, monitoring the brightness of all the stars in that little patch of sky, and if there's a planet that happens to be on an edge-on orbit, as seen from Kepler. Every time that planet passes in front of the star will seem to get a little bit fainter, and then it will go back up again. And so from this, we can find out the sizes of planets orbiting those stars, and we can find out the orbits of those planets, because that little dip is going to happen again and again and again every time the planet passes in front of the star. So if you know the period, the orbital period, then you can deduce the distance that planet must be from the star. And from there, you can start speculating as to the temperature of that planet and whether or not it's in the HAB zone. It might actually be habitable. This is the field of view of Kepler. It's about the size of your palm, held at arm's length. Happens to, in this particular field, which Kepler stared at for 3 years, there are more than 100,000 stars. And this is an illustration of the result. Lots of planets found in that field. Planets are just not rare, even small ones. So, you know, there are thousands of planets that Kepler has discovered, and most notably, small planets have been discovered more and more as time goes on. So in the last year or so, the greatest harvest of planets has been for the smallest ones, Earth-sized and what we call super Earth-sized planets. Just a little bit bigger than the Earth. And super Earths or mini Neptunes, that's a really interesting category of planet because we don't know what it's like. We don't have an analog for that in our own solar system. Could they be habitable? Are they just like really big Earths, or are they like really small Neptunes? Don't know. So really interesting finds. But they're doing the statistics on everything that Kepler has discovered and the other methods as well to date. Something like 1 in 5 stars has an Earth-sized planet in the habitable zone. That's the latest published number. There's some uncertainty in that, but you know, if we can just imagine that, how far we've come in the last 20 years from having no planets at all that were known orbiting other stars to now you can walk out and look up in the sky and pick 5 stars. One of them probably has a planet, and furthermore, it's an Earth-sized planet and in the HAB zone. So that's just a really striking realization. Humanity is different now than from what it was 2 decades ago. We are in a different place as far as understanding how we fit in the cosmic story. One of the questions is, has Kepler already found habitable worlds? And despite the media's glorification of every single thing Kepler ever does, it would seem that, well, here's one example. This is a good example, and some of you may have heard, this was in the news recently, Kepler 186f. So this is the first Earth-sized planet that is in the HAB zone of a star. It's orbiting an M star, so, you know, is it a snow cone? I don't know. But it's not a sun-like star, but we're getting there, because before that, the planets that were being discovered, maybe they were Earth-sized, but not in the HAB zone, or maybe they were in the HAB zone, but they were a lot bigger than Earth. So, you know, there were just a lot of unknowns and not really analogous to our own world. But this is as close as we've gotten, I think, to date, to being able to say that we have a real Earth analog potentially around another star. So, but the thing is, Kepler does not give us what we need in order to really characterize those planets and know what are they like. You know, do they have water on them? Do they have weather, continents, oceans, etc.? Kepler gives us the size and the orbit, and that's it. So we have to use our imaginations from there. And all of these pictures that you see in magazines or in the news views, they are all artists' renditions. We do not have the data that we need, and out of the artists' imaginations. Really, we don't have the data that we need in order to speculate, even in an informed way, what these planets are really like. In order to do that, we need to see the light of the planet directly. Either the planet has to emit its own light, or we have to see starlight reflected off of it. And this is an example of the state of the art. So this is a star system that has 4 giant planets in it. Okay, these are big planets, and they're very young, and we're looking at them in the infrared, and young giant planets glow like crazy in the infrared. So they're sort of the best case scenario. This is also a face-on system, not edge-on, but face-on. So we can actually, over time, watch these orbits, or these planets orbit around their star. It's kind of it's the ideal system to be using this technique on, but this is really the state of the art. And no observatory built to date is capable of doing this kind of thing for Earth-sized planets, but that's where we want to go. So this is my dream. What I want is a picture of a star, and I want to see around that star any little planets that might be there. This is a simulated image of what our own planetary system would look like. And what you see, that big dark ring, that is actually a hole in the donut-shaped hole in the dust of our solar system, carved out by Neptune, the influence of Neptune. Which is interesting all in itself, because maybe if you can't actually see Neptune, you could still deduce that it's there just by the effect that it's having on all the dust in our solar system, which we can see. And if I zoom in a little more, then I can actually see Venus, the Earth, Jupiter, and Saturn. Mars is not in this image because it's too small and faint. But we can see the other planets. And if I could get my hands on that speck of light, I might be able to characterize it and say, hey, that's a living planet just like ours. And then, we'd have spaceships and they'd be going there. That's actually, I don't know if I should go down that tangent right now. We can talk about that later. Spaceships. Okay, so in reality, what we're not going to be getting is a beautiful resolved image of the Earth, of an Earth-like planet with continents and clouds, and then we can look at the little life forms and say, oh yes, it's raining today on, the whatever continent. What we're going to get is a dot, a point of light, and a lot like this one. This is actually a picture of the Earth. I think this was Viking that turned, no. What'd you say?
Voyager.
Voyager, thank you. That turned around and took a portrait of the solar system. And there was the Earth, a speck, just a speck of dust, a mote of nothing. And Carl Sagan waxed very eloquently about this. This is where everyone you've ever known has lived out their lives, and everyone that has ever lived, and wars have been waged. Every life form that we've ever heard of over the eons has carried out all of its existence on that little speck of dust. So what does that get me? If I can get an image like that of a planet around another star, where does that get me? I think it actually gets me pretty far. So remember that light, that Earth light that was lighting up the dark side of the moon that I showed with the crescent moon? We can study that light to learn what the colors of the Earth look like from outer space. And 90% of what astronomers do is, they don't just look at points of light. They get a prism out and they break that light up into all of its colors. And the colors that come out tell you what that thing is made of, amazingly. I mean, that's just like incredible. We from a point of light, all I have to do is split it up into its wavelengths, and I can instantly see, this squiggly blue line, to me, is like screaming habitable planet. Because what it's showing, the shape of that line is showing, over here we have optical light, and then we go into infrared light over on the right-hand side. And those big, huge dips that you see coming down, those are water bands. Those are famous water bands. The Earth's atmosphere is very opaque at those wavelengths. if you had infrared eyes trying to look at those wavelengths, you'd have a very hard time seeing the stars at night. But then the Earth gets very bright as you go up into the blue, because we have Rayleigh scattering in our atmosphere that causes a blue sky. And there are so many other interesting signals in here too, like the vegetation, the plants, they're actually very dark in the optical, but then there's a bump up into the infrared, and plants become like white in the infrared. They're so bright, very reflective. Why that is, I don't think anybody's quite sure. But maybe that serves some purpose for them. So that's a signature of an organism that is harvesting stellar photons in a certain wavelength range in the optical. And then there's signs of oxygen and ozone as well, and even methane from little methanogenic bacteria that is very intriguing, because the simultaneous presence of oxygen and methane indicates that our atmosphere is strongly out of equilibrium. We are in disequilibrium. There are competing sources going on, and oxygen does not have a way of being produced as prolifically as it is other than photosynthesis. So on our planet, the presence of oxygen, especially in the presence of methane, is a giveaway that there's a life form here. Last thing I'm going to look at here is, I think if I tap this again, it'll work. Yeah, so this is not CGI, this is real data too. This is from the Messenger mission, which had an Earth flyby on its way into Mercury. And what we're seeing is all the different faces of the Earth. I wonder if I can actually go back and play that again. Can I go back? No? Okay, there we go. Yeah, I just imagine that all of that light was compressed down to a single dot. What would it look like? What you would see is, as continents and oceans and clouds come in and out of view, it would still just be a dot, but you can imagine the brightness of that dot and the color of that dot and the spectrum of that dot changing over time. And as the planet rotates and the same face comes back and back and back again, in principle, I should be able to make a map of that planet. It would be a rough map, but it would be information that would tell me there is an ocean on that planet that I'm seeing again and again, and it's glinting starlight. And there is a dark continent full of, something really dark, for example, plants that's coming in and out of view. And there are clouds that are changing over time, and maybe even seasonal changes you'd eventually be able to pick up. So that's my dream, and I'll just leave you with this thought. We are a speck of dust floating in the vastness of the cosmos, but there are more living organisms on this planet than there are stars in our entire universe, including all of those galaxies that we see. So we may be small, but we are filled with life. And if that kind of diversity can inhabit just one little speck of dust, imagine what is possible in the rest of the universe, and imagine what we will find if we can actually carry out a mission like this. Thanks. So now I pass the baton.
Okay, thank you, Maggie. That was inspiring. I am inspired. That was a beautiful blue sky vision of what we want to do. So now I'm going to rain on the parade. But I want to just remind people, plants need rain as well as sun in order to grow and to bloom. And so hopefully the rain I am going to shower on this will end up will grow the mission into a strong oak of a mission. All right, so just remember, I'm here to do good. That being said, okay, so the technical challenge of actually doing all of that stuff, that wonderful stuff, of looking at light that's coming from an exo-Earth around another star, is probably one of the hardest technical challenges that astronomers have ever even tried to do or even thought about doing. And I'm going to go through 4 reasons why that's the case. Okay, so as Maggie touched on, the stars are really far away. Okay, we're used to looking at the Earth as what we call a resolved source. We can see it's a disk, not a point. It's got character. It's got clouds, it's blue, there are continents. Okay, even when we look at, even when we move to the moon, we're still looking at a world. It's a world with character. We can really, we can see it. But as Maggie pointed out, even when we go as far as Saturn, okay, so we're out to the distance of Saturn, and do you see? Yeah, can you even see the? Can you even see the little arrow that's pointing to the little dot?
Yeah.
That's the Earth. Yeah. Okay. So we're already, even when we're still inside our own solar system, the Earth is just a little dot. And then let's consider this. Okay, the very nearest stars to the Earth, Alpha Centauri A and B. All right. So Saturn is 90 million miles away. Alpha Centauri, 26 trillion miles away. So what did I do this? Okay, so if the distance, thanks. So if if you make the distance from Alpha Centauri to the Earth, if you make that into the distance between New York and LA, then the distance between Earth and Saturn is like 2 football fields. Okay? And that's the very nearest star system to the solar system. So Earth at interstellar distances is really a really unresolved little fuzzy blue blob, pale blue dot, if you want to sound more inspiring. I tend to think of it fuzzy blue blob. Okay? All right, second problem. The Earth's bloody faint. Okay, and so Earth is 10 billion times fainter than the sun at optical wavelengths, and it's hard to get your head around how faint that really is. So I scratched my head and tried to come up with the correct analogy. Okay, so the Luxor skybeam coming out of the top of the Luxor Hotel in Las Vegas is the brightest light in the world. And so if that's the sun, the Earth is 4 candles, 4 little like dinner table candles. So brightest light in the world, 4 dinner table candles. Okay? And worst of all, those 4 dinner table candles are sitting like on top of the sky pyramid thing, of the Luxor pyramid. It's really close to that incredibly bright source. Okay, so the sun at 33 light years away, which is actually 10 parsecs, which is the astronomer's favorite distance. At that distance, if the system was this far away, the distance between the sun and the Earth is 0.1 arc seconds. Okay, that's the astronomer's unit. All right, so what is that in some kind of human scale we can actually comprehend? Okay, so 0.1 arc seconds, that's about the width of human hair. So human hair at the distance of 2 football fields. Okay, so Earth next to the sun to, human hair, 2 football fields. Imagine how close together those 2 objects are. And one of them's crazy bright, and the other one's crazy faint. That's a problem. Okay, and then here's the other issue, the last issue I'm going to talk about, which Maggie alluded to, and that is the solar system, in between the planets of the solar system, it's filled with junk. There is tons of dust in interplanetary space coming from comets and asteroids. So every time a comet in the solar system comes in towards the sun, it produces gas and dust. That's the comet coma and the comet tail that you actually see. Now that dust doesn't just disappear. It spreads out and it fills up the inner solar system and it produces the solar system's zodiacal light. So people, astronomers who've been to really dark sky sites, you can see the zodiacal light in the sky. It's like sort of this band of light reaching up at sunset from sort of the sunward direction is down here, and it marks out sort of the ecliptic plane, the plane of the solar system. So this is all comet junk and asteroid junk, and it's something you would expect to happen in a planetary system that has planets in it, because planets are actually originally were made out of comets and asteroids. They're the building blocks of planets. You expect them to be there. And in fact, we see this kind of dust at much higher levels around lots of stars. So this is Fomalhaut. So this is a well-known star. It's been known to have this massive disk of dust around it. This is truly massive, actually, and it's coming from a big, gigantic Kuiper belt, but much, much more massive than the solar systems. Now, it's true, this is a relatively young system, and the number of comets and asteroids in a planetary system slowly goes down with time. But still, there are plenty of stars out there that are just as old as the sun that have massive belts of comets and asteroids around them. So that dust can hide the planet. Okay, so here's another simulation of the solar system seen face on. The sun has actually been taken out of this. And so after the sun, the most conspicuous thing about the solar system is this huge haze of dust, of light coming from dust that scatters out, from asteroids and comets. So, and as Maggie alluded to, in the outer part, this dust is coming from Kuiper belt objects. And then in the inner part, this dust is mostly coming from comets. And so, this is pretty bright. The Earth, Venus, Mars are, just barely sort of peaking out in brightness over this haze of dust. If this dust was much brighter, even a little bit brighter, you wouldn't be able to see anything here. Okay, so in sum, observing an exo-Earth is like seeing 4 candles a hair's width away from the brightest arc light in the world, from 2 football fields away in a dust storm. All right, so that sounds really bad. Hopeless? By no means. And so now we lead into Jeremy Kasdan, who is going to tell us how to get this done.
Okay, so I get to do the engineering part, which is fun. So before we talk about solutions to this general problem called high contrast imaging, we need to learn a little bit about telescopes and optics, just a little teeny bit. So, wait, I shouldn't have touched it twice. So this, I think most of you have seen this picture. This is the Hubble Space Telescope. So this is going to be our canonical telescope for the conversation. I didn't use this. Oh, I guess not. No, I did turn on. It's good. Oh yeah. So this is our canonical telescope for the discussion. It's about 2.4 meters in diameter. Many of you have seen pictures of it. We need to learn a little bit about how this telescope actually takes images and why stars look the way they do, which is essentially like this. So this should be a fairly familiar picture to you. This is actually a picture of Proxima Centauri, which is the 3rd star near Alpha Centauri A and B. The Alpha Centauri stars are actually too bright for Hubble to take, but this one it can take. So the question is, why does it look like this? And this leads us to everything we need to know about how to solve the problem of high contrast imaging. And I remember when I first gave a talk to my daughter's 7th grade class many years ago. They just graduated this year from college, so this was quite a few years ago. I asked the question, what does this star look like? And it takes a little bit, and you sort of talk about it for a while. And eventually people will say it looks like that. It has these big lines that are sticking out of it, and it's a big blob of light. But of course, the interesting question is, why does Proxima Centauri in this picture have these bright lines, but these don't? And these are much smaller. This is really big, and it has all this other stuff going on here in different colors. And these don't look like that. Of course, they're dimmer stars. And so if we can understand that, we understand everything about high contrast imaging. So this is all examples of what we call diffraction. This is all a diffraction problem. That's the key. So the way to understand diffraction is to think, I like to think about it in terms of something you all remember, which is water waves, right? Light is a wave. So if you think about whenever you've been to a pond and you drop a stone into a pond, or toss the stone, what happens to the water, right? If I just drop a rock in the water, you start to see ripples sort of spreading out from where you drop the rock. These little circles, these are waves, right? You generate waves, and the water waves go traveling out bigger and bigger. If you think about getting really far away from where you drop the rock and look at a little piece of the water waves, it looks like a flat wave, like when you're in the beach and waves are coming at you. Light is the same way. These stars are really far away, and they're radiating light as waves in spheres now instead of circles, and we're really far away. So when that light gets to us, it's a little piece of that sphere right? So this is a common experiment. Some of you who took high school physics may remember. You got a little slit in a wall, and here are the waves, right? So it's like taking those water waves, but just a little piece so they're flat. So that's what light from stars is doing when it actually gets to us. And this is my telescope opening, what we call the aperture. And you can see the waves don't just travel in a straight line in a little tube here, right? They diffract around the edges and they form these little semicircles and they interfere with each other. So we got bright ones, dim ones, bright ones, dim ones. We call this a diffraction pattern. This is what waves do when they pass through an aperture. It'd be great if they just went straight. Then we put a little lens here or a big mirror like in the Hubble telescope, and it would all come to a focus to a little point. But that's not what happens. So this is the whole problem, is that when the waves go through the entrance of my Hubble Space Telescope, they form these patterns when they get to the image. And those patterns look like this, right? So if I have a circular telescope, what I get are these little, see these rings? You can just sort of see these rings of light. They're equivalent to these lines that are coming out here, these different colored patterns. That's what light does when it enters a telescope. It forms rings. The image of the star has these rings that get bright, dimmer and dimmer as it comes out. And this is the big, bright center. So why is it that these are small, but this is big? Well, it's because this is so dim, we haven't been integrating long enough to see the rings. This looks just like this. It's just this other structure is so dim, we're not seeing it in the scale of this picture, right? So that's why bright stars look really big from a telescope, and dim stars look really small. We're just seeing less of the what we call the point spread function of the star. So does anyone know what this are? Why do we see that? Why do we all think that stars should have that? Does anyone want to venture a guess? Who's not here with my group? Nobody has a guess? Well, do you know what the Hubble telescope looks like? If I look down the front end of the Hubble telescope, does anyone know what I would see, what it looks like, the structure of the telescope? Who wants to guess? It looks like that, right? So there's that circular entrance to the Hubble telescope. And then if I go back, right, light comes in here, and there's a big mirror, a 2.4 meter mirror here. Instead of a lens, it has a big primary mirror that we call the primary mirror to focus the light. But then it would just send the light back out the front of the telescope. So how do we get the light back down to where all the instruments are that are down here? Yes?
You have a smaller mirror in front of it that reflects the light down to the point.
Exactly. We have another little mirror right up here that sends the light back to where all our cameras are. Do you know what that mirror is called?
Secondary mirror?
Secondary mirror. Excellent. Absolutely. So we have a secondary mirror, right? Well, how do you hold that mirror up? It's not just floating out in the middle of the telescope, right?
From the imagery, you had that.
That's right. Hello. So you have to hold that, hello? You have to hold that mirror somehow. And that's what these are. We call them spiders. They're just metal struts that hold this other mirror in the middle of the entrance of the telescope. And that's what causes these. Those are called diffraction spikes, and they're simply caused by the telescope. So everything, the message here is everything we see when we imagine imaging a star is through the telescope. It has nothing to do with astrophysics or astronomy or what stars look like. It has everything to do with the telescope. Change the telescope, stars will look completely different because they're really far away. So as both Aki and Maggie pointed out, they're just points. They're little teeny points of light. So this is the problem, right? So now let's get back to what Aki and Maggie were talking about. What if we had an Earth really far away and we imaged it with the Hubble Space Telescope? Let's forget the star for a second. What's it going to look like? Well, it's one of these dim things because it's really, really dim and it's really far away. So it looks like that, right? So all you're seeing there is that center big lobe of what we call the diffraction pattern through the telescope, right? Because it's really an infinitesimally small point of light. This is due to the telescope. But all that other structure, the rings and the spikes, too dim. We didn't collect enough light to image them. So that's what the Earth would look like. That's our pale blue dot. Now let's put it next to a star, what Aki showed. So what we're going to put up here is what Alpha Centauri would look like if we were imaging an Earth next to Alpha Centauri. And we could actually do it with the Hubble telescope, which we can't because we would burn out all the detectors inside the telescope because the star is so bright. But if we could do it, it would look like that. Right, so this planet's now gone. So that's the problem. Remember Aki told you about how the planet's really dim and really close. It's inside that diffraction pattern of the star. You hear those rings, that here's the spikes due to the Hubble Space Telescope, and right there is the planet completely, it's about 1,000,000 times dimmer than this ring that's right over it. So, there's so many photons coming from the star here, 1 in every 1,000,000 of them is from the planet. You can't see the planet. This is the problem we have to solve when we talk about high contrast imaging. How do we pull the planet out of there? There's only 2 solutions to this problem. One solution is we'll change this. Remember I said that stars look that way because that's what the telescope looks like. Change the telescope, we can change this pattern. So maybe it's possible to pick a different shape, change the optics, do something so this looks different and all this light isn't there. I work on that. I have a lot of colleagues working on that. There's a lot of techniques out there to do that, and to varying levels of difficulty. But there's a second way. What if we just get rid of the starlight? If we can somehow eliminate the starlight, then none of this is there to diffract through the telescope. Get rid of it before it enters the telescope, and all we're left with is this previous image. Just the planet, because I got rid of the starlight. So those are the 2, and people have known this since the 60s, that these are the 2 ways, actually earlier, since the 20s, that these are the ways to image something. It's just we've been working on the technology ever since. So we're going to talk to you today, and what we're here meeting about this week is a particular technology to do this, which is the second thing. How do I get rid of all this light to image the planet? So the inspiration is a solar eclipse. So this is an eclipse, a picture of eclipse. This is the moon passing in front of the star. And this is what inspired the whole ideas that we're here to talk about today. This is actually the solar corona, right? That's something we normally don't see because the diffracted light from the sun is so bright, it swamps out this gaseous corona around it. But if we can block the light from the sun, then we can see the corona. This is how astronomers have been studying the solar corona for a century, is by waiting for lunar eclipses to pass in front of the sun. So how does this work, and how does this inspire us to image exoplanets? Well, what's going on is this is a slightly different view of a solar eclipse. Rather than looking at the sun with the moon in front of it, I'm looking back at the Earth, at the shadow that the moon casts, right? So it's important to think about this is why an eclipse works, to let us see the sun, right? It's exactly the same as if I put my thumb up in front of that light there, and now I don't see it, right? So what am I doing when you've all done this, you've been in the car and the sun's in the way, you can't see the traffic light, you go like this, right? Well, what are you doing when you do that? Why does that work? Want to answer that question? You're creating a shadow, right? You're casting a shadow from your thumb into your eye, and now you can see something dimmer because you blocked it out, which is exactly what's happening here. So what if we put a telescope right in this shadow? Well, the sun's not getting into the telescope anymore. The light never entered the telescope. That's what we were setting out to do. So it was actually in the early 60s when this was first suggested to image planets by Lyman Spitzer at Princeton. He's considered the founder of the Space Telescope. He was the first to propose putting a big telescope in space, which later became Hubble. In that same paper, he suggested we could image planets by doing this, by putting up a big screen in space, blocking those waves of light from the star so that we can then see a planet in front of it. In other words, cast a shadow and fly the telescope into a shadow. And this has been worked on ever since. On and off, people have looked at doing this. So this is just a simple diagram of how this works, right? So here's your star, radiating in every direction like I described. You're really far away, so the rays of light are coming at your telescope. You could imagine these as waves if you like as well. And you put a screen here that blocks the rays, casts a shadow, and here's your telescope. And so the idea is I want to see this planet that's really close to the star, as Aki described, right? So that sets this whole geometry. If I have a telescope, 2.4 meter telescope for Hubble, say I make this about 4 meters, so I leave a little room to slop this around. Well, that defines, so then I take that 4 meter screen and I put it far enough away so this angle lets me see the planet that's 1 astronomical unit away. You can ask the question, well, how big is that? Well, that turns out to be about 10,000 kilometers. So you're starting out with a pretty large-scale thing, just thinking about it geometrically. I got to put this screen 10,000 kilometers away from my telescope and hold it there to within about 1 meter so it stays in the shadow, and then maybe I blocked all the starlight and I can see the Earth. Well, that would be really cool, and it would look something like this, right? And there are no planets because it doesn't work. And that's why it's taken us 50 years to figure out how to do this, right? Because we haven't fixed the diffraction problem yet. So remember we talked about the reason stars look the way they do is because those waves of light are hitting the circular opening of the telescope and creating that diffraction pattern. The waves are bending. Well, this is just the opposite of that. Instead of a circular opening, it's a solid disk, but it's exactly the same problem. So the waves of light from the star now are bending around it, just like they would if you had a rock in a pond and the waves were coming around, hitting the rock. They bend around it, right? You don't have a little, column of no waves, right? And it completely makes this not work. You end up with almost as much light in the telescope as before you had the shadow. Not quite as much, maybe 100 to 1,000 times less. But when you look at a shadow, like from an eclipse, it's not a very dark shadow. It's dark enough to do a lot of things, but not to find planets. So the amazing thing is Lyman in the 60s knew this. He figured this out. This was well known. And he suggested the solution. The problem was nobody knew how to make it until today. And the solution is you don't use a solid circular disk. And there have been a lot of ideas proposed, but this is our favorite that we work on. You make it look like that instead. And essentially you're controlling how much light is coming past this disk as you move out radially by the particular shape of these petals. And if you get this just right, then you can create a dark enough shadow where you've eliminated all of the starlight, and lo and behold, you see planets, although they would really be little dots of light. We'd be really lucky to see them that highly resolved, but it's a nice picture. And at some cost. Remember when I showed you the little geometric picture, I said, well, you have a 2.4 meter telescope, so I'll make the screen about 4 meters. Well, the problem is that doesn't really work because of this diffraction problem. In order to make it work like this, you have to make it a little bigger. So this ends up being about 30 meters, and it ends up being about 30 to 50,000 kilometers away. So this is, this can be roughly the size of a football field, maybe, half a football field, depending on your science. And this is really far away. So now it's just a really cool engineering problem, is you have to build this big screen that looks like that. These petals have to be this shape to roughly the width of a human hair. And you've got to control this telescope to stay within about a meter of the line of sight, over 50,000 kilometer distance. And you got this thing is big. It's bigger than any rocket that we have. So you have to figure out how you fold it all up, put it in a rocket, launch it off the Earth, and deploy it. So this is the fun part. This is the cool stuff. So we've been working on this now for probably 7, 8 years. Most of the work's being done at JPL. Many of the engineers who are working on it are here. And so I'll show you well, first thing I'll show you is what this design looked like. So these, actually, the fellow who came up with this is just sitting right over there, Mark, he's a brilliant engineer, came up with a design that could do everything I just said. And it looks something like this. So it all starts rolled up around a satellite. The starshade and the telescope separate, the starshade unfurls, and then it expands. So now it looks like what it's supposed to. It flies away. The satellite is going to fly in the shadow, and what you're seeing is the starshade sort of comes across the star, creates the shadow, and boom, you get to see the planets. So that's the concept that we're looking to actually build and fly in order to image planets, and we've been slowly, incrementally studying the engineering of this. So I'll show you 2 pictures, one picture, one movie. The first thing we wanted to make sure we knew how to do was actually build these petals. So this picture has about 20 petals arrayed around here. As I said, these have to be right to within about the width of a human hair. And these petals are 6 to 7 meters long. So there's an example of one there. That's about 3/4 the size of a real petal that we might fly. So you have to make the real one be even bigger than that. So this is a picture of one we made about 4 years ago. This is both the same petal. This gives you different views of it. There's Maggie, Aki, and Sarah Seeger's chair of our team in the back of the room there somewhere. I guess I should do this so I can see you. And so we built this petal, we measured it, and this petal was good enough. This was accurate. The shape of this edge was exactly what we wanted it to be, to less than about 20 microns, which is not far from the width of a human hair. So we proved we knew how to do this. We knew how to make one of these things. The next step was to show we knew how to make a bunch of them roll them up and fold them around a hub and actually deploy them. Once this thing is deployed, those petals have to go to where they're supposed to be to less than a millimeter, which is very precise and has to deploy that way every single time. So that's what we did. So about 3 summers ago, 4 undergraduates, 2 from Princeton and 2 from MIT, went to JPL. That's Mark, that's Doug Listman, that's Dave Webb. These are the 4 undergraduates. Built 4 of these petals, which you can see in the background. That's one of them. That's a spare one that they built. And then what we did is we delivered those to Northrop Grumman Aerospace Systems in Santa Barbara, California. And we attached it to a mock-up of the hub, rolled them up, and we showed that we could deploy them. And this was an example. This is one of the first runs of that experiment. So you can see them unrolling. So there's only 4 because it's expensive to make 20, and 4 showed what we wanted to show. So then they locked into place. Now this shows that deployment. You can see just like in the animation how the petals flatten out. And boom. And so that was speeded up. That whole thing takes about a half an hour or more. But the base of these petals went to exactly where they were supposed to go. We did this 15 times, and in 15 times they went to where they needed to be, less than a millimeter, which convinced us we can do this. We know how to do this. So that's a picture of me in the clean room in front of the petals. And so this is now an ongoing project at JPL and at Princeton, NASA, and other places to demonstrate that we can actually build this and make it work for a mission. And the goal, of course, is to see a picture something like this, which is a totally different version of what Maggie showed you. If we can get this to work into space, this is a picture of our solar system through an occulter like that with a 4-meter telescope, not a 2.4-meter telescope, bigger than Hubble. And that's what's left of the sun after you've put the Starshade in. So even with all this effort, it's not perfect. It hasn't eliminated 100% of the light. Some of it still diffracts around. But now it's much, much, much dimmer. You can see the planets are dimmer than the sun in this picture. And you get the Earth and Venus. I think that's Saturn. That's Jupiter. That's Jupiter, right? Oh yeah, that's Neptune. Thank you. So that's the kind of picture we want to see. In particular, we want to see the Earth, which is right there. And I give a lot of credit to JPL that they made the animation and the film, the deployment, of course, did most of the mechanical engineering work. So that's the story of using starshades to image Earth-like planets. And we're all hopeful that sometime within the next decade and a half, we'll have a mission in space, and you'll be able to open the newspaper and see that pale blue dot that Carl Sagan talked about. But it won't be us. It'll be somebody else. Thank you.
Yeah, let's thank our 3 speakers once again, and I'd like to introduce a few more team members so we can begin our panel discussion up front. So yeah, let's thank our speakers one more time. So again, we'll have a panel discussion here, and then following the panel discussion, we'll go upstairs to the Welcome Gallery of the Granger Theater to continue the conversation. So I'd also like to introduce Dr. Sarah Seeger. She's the chair of the ExoS Science Definition Team. Dr. Seeger is an astrophysicist and planetary scientist exploring the possibility of life throughout the galaxy, adapting the principles of existing planetary science to the study of exoplanets, planets outside the solar system. She is quickly advancing a subfield initially viewed with skepticism by the scientific community. While continuing to create and refine theoretical models of exoplanet atmospheres and interiors, she is also spearheading advanced hardware design and space mission projects, including ExoplanetSat, a university collaboration to build low-cost nanosatellites to observe planetary transits. I'd also like to introduce Dr. Sean Domagal Goldman. Dr. Goldman is currently a research space scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. His research is on exoplanet characterization lessons from the pale orange dot that was the Archean Earth, the ancient Earth. You can also find him blogging about baseball stats and the woe of being a Cubs fan at Bleed Cubby Blue. Dr. Mark Kuchner is an astrophysicist at NASA's Goddard Space Flight Center. Together with Wesley Trout, he invented the band-limited coronagraph, a planet-finding tool to be used on the James Webb Space Telescope and the WFIRST telescope. An expert on exoplanets and debris disks, Kuchner helped popularize the ideas of ocean planets, carbon planets, and helium planets. And he now serves as the principal investigator of the popular citizen science website, discredit.org. And Mr. Mark Thompson has been developing large deployable structures and mechanisms for space for 32 years. He has invented and led the development of 10 deployable antennas with aperture diameters of 9 to 15 meters. Mark is also the inventor of the 34-meter diameter Starshade he is developing at JPL with his exoplanet colleagues. His role is to advise the team of Starshade capabilities, performance, cost, and the trade-offs associated with the different spacecraft and mission configurations that are being considered. Well, I'd like to invite all of them to come up here and join us for this panel discussion, please.
Thank you, Sarah.
Musical chairs.
Great. Well, do we have this? Yeah, we have it on now. Well, I think at this point, let's open to questions from the audience. If we don't have any, I have a couple myself. Any questions? Yes, right up in front here.
How do you envision deploying this? I mean, so would it be within our solar system or sending it out of the plane, or how do you expect that to work?
Yeah, it would not be in Earth orbit. There's a whole variety of reasons why this system would not work in Earth orbit. So there's really only two places that we've talked about putting it. One would be what's called the Earth-Sun Lagrange point, L2 point, which is actually where the WMAP spacecraft is right now, and it's where the James Webb Space Telescope will go. It's about 1.5 million kilometers away from the Earth. The other spot, which is our favorite spot at the moment, is in what's called an Earth-leading orbit. You can either Earth-trailing or Earth-leading, both work, which essentially means it'll be in the same one astronomical unit orbit around the Sun as the Earth is, but just a little bit in front or a little bit behind. And it's where the Spitzer Space Telescope is right now. So that gets you away from the thermal influence of the Earth and the gravitational attraction of the Earth. It's a very stable environment. There are plenty of launch vehicles available that can do that.
But to answer a little more directly, definitely in our solar system, we only send things far away if we want to visit another planet. The Voyagers and Pioneer Voyagers actually went accidentally past our solar system, but we're talking about close enough to Earth so we can communicate and not get too far away.
Do we have another question? Yeah, we do, up in front here as well.
Yeah, how would the Starshade move along also if you're directing it towards different stars?
Yeah, that's a very good question. It's you have to thrust it. It has to fly over the sky. Well, one of the two, the Starshade or the telescope, has to be moved so it stays in line. There has to be one line between the star, the Starshade, and the telescope. So it'll be equipped with thrusters that'll fire and fly it around the sky to do that.
We have a...
And to add to that, I find an interesting thing about the design that we're talking about with our probe class mission. We're actually looking at flying the telescope around and keeping the Starshade in one place, because the Starshade is so
pretty much you fly whichever one is lighter because that requires less thrust. And what happens is the mission duration ends up being largely determined by how much fuel you take up. When you run out of fuel, the mission's over because you can't.
Right, and just to add, because we did kind of forget to mention this, we weren't trying to sweep the hard parts under the right purpose, but it takes a few days to a week to retarget. So after you finish looking at one star, it takes a while to retarget, and then you may want to move back or go somewhere else.
But we try to sell that as a strong point for especially the bigger, like flagship class missions. If we were ever to fly like a big space telescope with the Starshade, we started trying to turn that into a feature because for 2 weeks in between every target, you can do all kinds of other astronomy because the Starshade is out of the way.
That's a feature for our colleagues in other areas of astronomy, right? So we're trying to convince them to get on board with our mission, and we say, well, you guys are going to have 2 weeks every time we retarget.
Yeah, look at all those things like galaxies and crap, you know.
Astronomy, real astronomy is what they'd say.
Spectrometer attached to this?
Yeah.
Yeah, there'll be both an imaging camera and a spectrometer.
So those slides that Maggie showed with the different colors and the features from oxygen and ozone and methane and carbon dioxide and water and plant pigments, those slides were all spectra, synthetic spectra, and essentially that's what we'd be
Actually,
using spectrometry.
that was real data.
Those are real data.
Yeah, from yeah.
You have to think of them as being a synthetic spectra of an exoplanet, I guess I should say.
We have a question in the back.
Hi. I have a question for one of our Twitter followers. Would this 50K separation concept be restricted to one field of view, or could both shade and scope rotate to new targets?
That's sort of the similar to the question he asked. If we move the telescope, as what Sarah and Maggie were saying, the Starshade just needs to change its orientation. It just needs to repoint so its center is directed at whatever star you want to look at, similar to the Hubble telescope. And then the telescope does have to be moved around the sky to get to different targets. So over the course of the year, when you go around the sun, pretty much the whole sky is available to image for planets, but each star has a particular time of year that you can see it.
Let's see, I see a hand up in the back corner there.
In what wavelengths of light would this telescope be able to see? And do we know what telescope will be using?
Oh, that's a great question. So we're going to operate at visible wavelengths to start with. The bigger a region of the spectrum we could possibly cover, the happier would be. But we're going to start out with wavelengths that are similar to those your eyes can see.
There's another question in the back.
Is this going to be an American effort or an international effort?
I'm not a scientist and I'm not sitting up front, but I get to work with them. And so NASA will look at this as a study currently as an American effort, but the possibilities always exist when NASA plans a very exciting science mission when we move past the planning, the conceptual stage, into the possibilities of implementation, to look and work with our international partners. Frequently we work with partners in Japan and in Europe, and that would almost certainly be the case again here, should this idea prove to be scientifically compelling and technically feasible. And we're starting to see from the work. Yes.
Yeah.
Some of the work that we're doing here this week and some of the presentations this evening that just might be.
So just to add to that, right now the United States is the only nation really pursuing the Starshade heavily, and I think it's fair to say we're the world's experts here on the Starshade. The telescope itself, as pointed out, could be an international partner could launch that, and in fact they could then rendezvous later in space.
Although I will add that for a while, we were encouraged to avoid using the phrase formation flying because it sounds very complicated and risky and expensive. But ESA, the European Space Agency, is launching a mission to look at the sun with a starshade, and it's just a regular round starshade that will fly in front of the telescope. But they're bragging about it as the first ever formation flying mission. So we're actually going to point to them as a form of heritage for what we're trying to do, which is much more complex than that. So we're definitely leading the charge in America for trying to find Earth-like exoplanets this way, but the Europeans they're doing it. They're flying a starshade.
Although we should say that
sunshade.
Sunshade, but the Europeans have lined up their major astronomy missions for the next couple decades, and they aren't planning to do direct exoplanet imaging. That is on the table for NASA, but it does not look like it's on the table for the ESA is the European Space Agency. That's our European counterpart for the European Union. So unless another nation were to step up, it's almost certainly going to be the U.S. in the lead. And as a NASA scientist, I think that's cool because that means I get to be a part of it. As an American, that makes me pretty damn proud because I think it's cool to be out front.
I'm going to jump in with a question here. What is the single biggest hurdle that Starshade faces to being selected and funded and fly?
Budget.
Yeah, that's an interesting question. It wasn't.
Well, I think we should let Aki elaborate. Yeah, but I'll put it this way: we were given a charge, and we were given a budget for this. This thing can't cost more than $1 billion. That's not a lot of money for a space telescope, especially when you have 2 spacecraft. So I actually think our biggest challenge is staying under that price cap at the moment, and we're working on it. I guess we're working on it, but I actually think that's actually our biggest technical challenge, to get this done as cheaply as possible in every single aspect.
I'll add to that a little bit. I came into this activity kind of skeptical that this was technically feasible, and there is a perception amongst a lot of people in the astronomy community that it is technically infeasible. But because of the great work that Mark and Jeremy and Stuart, who's not here, have done on the engineering side of things, they've convinced me that this is possible from a technical standpoint, which means we're left with primarily challenges of making sure that it can fit into the NASA's programmatic plans for the future.
Yeah, I think I've been pretty convinced too. I think we could build this. I think we could make it work. But can we make it work cheaply?
And I think this $1 billion may sound like a lot of money, right? I think it's probably no one in this room has access to $1 thumb we give is that everything in space costs 100 times what it does on the ground. And here you saw there's 2 spacecraft, there's kind of 2 of everything. But I wanted to take the opportunity here to break in for a second and mention that in addition to all the things you saw, we didn't have time to talk about everything. But one really awesome thing that's happening, in addition to demonstrating that the petals can be manufactured and deployed to the tolerances required, people are doing what we call subscale testing, both in the lab and in the environment. And this here, the thing that Mag is showing, she can actually show how to block out a star.
Yeah, right.
Actually been used, this is one of the prototypes that's been used in the desert to test over long distances of about 3 kilometers to block out a fake star, an LED light, and to reveal a fake planet, and to show that we can reach the levels of contrast. So there's a ton of work going on, and we may have drunk the Kool-Aid and, well, I don't want to say we've brainwashed ourselves. We've convinced ourselves, and now we're trying to convince our peers that as a community, the community has tackled major problems in technology development, and there are ones remaining that we're now working on.
This is extremely dangerous, by the way. and it's because the tips of these are, manufactured to be. I mean, they really are. You saw the picture of us with the bigger one, and this one doesn't have the full tip on it up there, but it's very sharp. But come look at it.
It's basically a giant throwing star.
I mean, literally, when the final edges actually do have to be razor sharp, and they need to be angled like a razor too. So it really is.
Which is
razor big throwing star.
From a technical standpoint, that is one of the major challenges, right? Is making sure that the edges are sharp enough.
There are several. If you talk about what has to happen, there are several engineering technical challenges that have to be overcome, or at least proven, and that's what we've been doing. Since about 7 years ago, probably now. Right?
For me, just 4.
Yeah. And we're just incrementally going through all these things. And there's a program in place to do that, to show that we have under control all the engineering challenges. And one was to show we could make a pedal like that and do it accurately enough. We did that. One is to show that we can deploy them in a mechanism similar to what we do in space, do it accurately enough. We've done that. Another is what Aki and Sean were alluding to, is the edges of that. The reason they have to be so thin is because you can't have the sun reflect off the edges and go into the telescope. If you had a culture sort of with the sun over here, well, then it would just bounce off the culture and go into the telescope, and that would be bad. So you have to have an edge onto the sun. Then the problem is you don't want it bouncing off the edges and coming into the telescope. So you have to make them really sharp. So we're in the process of running tests. JPL's whole program in place, and we've been doing sample optical edges, and then we're going to make a whole culture out of like that. We have to verify the optics. That's what Sarah was alluding to. So we have a lab in Princeton doing that. There's the desert test to show that indeed we can shine light on one of these things and get 10 billion fewer photons. So there's a series of these things that are all happening.
One more point. This was my aha moment, right? When we were pressing the engineers like Mark and Jeremy and saying, well, what is the biggest challenge? And edge sharpness came up as like one of, I mean, you've got this thing, we're flying in formation, it's got to fold and hold its shape, and it was like sharpness. I was like, just, send some astronauts up there with knife sharpeners or something like when I hear that that's the big challenge, or one of the big challenges, that puts it in a achievable scale for me. I don't know why that is. It just seems like that's a much more doable thing than a lot of the other things people have had in their minds as
Plus, this way, if we find aliens and they turn out to be bad, we can chop them up.
That's right. Actually, that's the other thing too. To keep it more stable in space and not floppy. It is in fact spinning. The Starshade is spinning. While the observations are happening. So razor sharp spinning like a chainsaw. Not a chainsaw. These
sauce.
Buzzsaw.
Yeah.
Well, I think we'll take one more question from the audience, and then we'll break and continue the conversation upstairs. There's a hand up in the back.
Yes, how much of the sky could you see with this system?
That's a really good question. And actually, I was going to mention this because Jeremy was talking about sun glinting on the edges of the Starshade. There are huge regions of the sky that we cannot look at any given amount of time. We have to be a certain angle away from the sun, and we have to be a certain angle away from the Earth. We can't point right near the Earth either because the Earth is very bright. And then there are all these other constraints with reflecting light from the sun off of the Starshade into the telescope. And even Venus and Jupiter are problematic because they are very bright in the sky. So we have this whole region of avoidance where the allowable field of regard is this really bizarre shape. And it moves over time as the telescope orbits around the sun with the Earth. So that's evolving, and we have to choose our targets really carefully so that during the course of the mission lifetime, we can go from star to star to star in a really efficient path and observe as many targets as possible with the least amount of fuel and still stay inside this weirdly shaped allowable field of regard. And one thing that is kind of neat about being here at the planetarium that is, I don't know of any other science team that has really ever done this as a part of their serious mission. We're going to actually go in the planetarium tomorrow morning and try to visualize this. We will have all the stars in the sky, our targets highlighted, that allowable field of regard, and we're going to put ourselves in front of the Earth in an Earth-leading orbit and try to actually visualize that and understand more intuitively what that means for us over the course of our mission.
Yeah, I mean, it's worth understanding that related to that, it's not like Hubble where we're taking pictures of everything everywhere, the deep fields, billions of galaxies. There's only 100 or so stars that are close enough and bright enough that we could actually imagine seeing a planet. So we formulated these lists of stars.
What would you say, how much of the sky would you say is observable to us? Half the sky?
Over the
less?
course of the whole mission?
Well, at any given time.
Oh, at any given time, no. Less than half. Yeah,
less than half at any one time, yeah.
But over the course of the mission, we get the whole sky.
Yeah, I mean, yeah, right, half. Obviously.
Well, I think the question was, when we have the Starshade and telescope lined up, how much of the sky are we actually looking at? Or with the telescope?
Well, if we have an eye view in place, then it's only going to...
Yeah, I mean...
It's any arc length square, right?
Yeah,
it's like a square arc there.
Yeah, it's a very narrow field of imagery. We're only looking at a very, very small angle around the star that we've just blocked to see planets. That's all we're going to see in the telescope.
It's comparable to the size of the disk of Mars, for example.
And we'll do the disk of Mars like couple hundred odd times.
100 times the disk.
Once for each target we want to look at. And those targets will be spread out throughout the sky.
Yeah.
Well, once again, I'd like to thank the panel and invite everyone to come upstairs to the Welcome Gallery and continue conversations with the members of the Starshade team.
And just as
an FYI, we will be bringing the Starshade pedal and the smaller Starshade demo up there, and we hope that when we're up in the meet and greet area, everybody will come and take a look.
Well, let's give the team our thanks.